So we have concluded the proof of the first lemma, which, recall, was about the fact that the graph of every term function is in one of these Dn. We move on to proof by complexity of formulae that that if x is any set definable by phi, then the set x is in one of these Dn. That's our goal at this point. And so we suppose that x is defined by phi, and we are in particular focused on proving this for sets x that are empty definable, meaning that there are no extra parameters that we call w, that it's only these free variables v that define x. And if we suppose that phi has n free variables, that is to say all of them are sort of accounted by v, so to speak, that this is going to be a set of n-tuples, and we'll show that this set of n-tuples is in Dn. So for proof by induction on the complexity of phi, we start with the base case, which is that phi is the equality of some two terms. Between them, they must have n free variables, and the set that phi will then define is the same as the set of values which these two-term functions map the same inputs to the same outputs. And that's just by definition of, say what the term functions are and what it is to satisfy equality. So this set of elements, though, can be redescribed in terms of a certain conjunction, and because this is a conjunction, then this amounts to intersecting several sets, and we know that the set of all of these D's is closed under intersection, also union, so we get to use disjunction and so on. So by describing it in terms of this longer conjunction, where each one is individually the graph of one of the term functions, or just the equality of some two terms, then we have that each one of these, each one of the sets that we are intersecting essentially is in Dn, and therefore the intersection of them all is in Dn. A similar reformulation of a relation R in terms of conjunctions establishes the other part of the base case of this proof, and similarly, negations and negations are also taken care of in a similar way because we have closure under complement. Projections will take care of the case where phi is an existential quantification over some psi, and at this point I think that the basic method of proof is hopefully clear, so I'll skip the details here.